So we just started looking at the chain rule, and the chain rule is a great technique to help us take the derivative, especially when you have multiple functions, composition of functions there. And so I just rewrote the rules that we were using last class period. And there's just two different forms. They are the same thing. They're just written in different notation. So let me pull an example. And so maybe let's start one that doesn't have multiple things going on in there. How about f of x? This is equal to 12. Then you have a parentheses, 2x to the fourth plus 5, end your parentheses, and then that is all raised to the 3/4 power. So we want to find the derivative of each of the functions as follows. Okay, so we want to recognize what is the outer function and what is the inner function. And so looking at this outer function usually is outside. So what's not in the parentheses, but surrounding it right here. So we could say that our outer function, if we wanted to, y is equal to, if we were using this notation up here, f of u, which would equal this 12. I'm going to put u where this 2x to the fourth plus 5 is, 3 to the fourth. Where u is actually equal to the inside, so that's the inner piece, which is 2x to the fourth plus 5. So we can do it in pieces. We can use this formula and we can find out what dy du is. Okay, so looking at this, taking the derivative of y with respect to u, dy du is equal to 12, bring your power down front, times 3/4 u, and then subtract 1 from our power. So 3/4 minus 1. I'm going to write that 1 as 4/4 though. So you can simplify a little bit. I have a 4 in the denominator. That goes into 12 3 times. So we're left with 3 times 3 in front, which is 9. U to the, well, 3/4 minus 1, I'm sorry, 3/4 minus 4/4 is negative 1/4. And so now let's take the derivative of u with respect to x. So du dx. So using our power rule, bring our power down front and multiply it by the number in front. So 2 times 4. Subtract 1 from our power, so 4 minus 1. And then the derivative of a constant 5 is 0. So du dx is equal to 2 times 4 is 8 times x cubed. So by this formula, we got dy du, or f prime of x, is equal to dy dx, which is equal to dy du, which we found right here was the 9u to the negative 1/4, times du dx, which we found was 8x cubed. So when we use this form, this is where we have to go back and we got to go in and substitute what u is in terms of x. And we were given that, we said that u was 2x to the fourth plus 5. So this is equal to 9 all times u, which is 2x to the fourth plus 5, all raised to the negative 1/4 power, all times 8x cubed. So negative exponents, remember we can make those positive by bringing it down to the denominator. And it's in the form that we can do that. So let's bring down this piece right here, this parentheses raised to the negative 1/4 power down to the denominator so we can make that exponent positive. So we have a 9 in the numerator times 8x cubed in the numerator, all over 2x to the fourth plus 5, all raised to the 1/4. So 9 times 8, 72, x cubed, all over that 1/4 power. We can rewrite this as a radical. The denominator is what index you're taking. So we're taking the 4th root of 2x to the fourth plus 5. Okay, so that was the method using that one way. We can also do this by let's just go back and do it without breaking it down all like that. That's pretty much how we were doing it on Monday. So again, we had y is equal to 12, parentheses. Sorry, it was 2x to the fourth plus 5. All raised to the 3/4 power. Okay, so just taking the derivative, we have 12. We're taking the derivative of the outer piece. So we're just gonna bring our power down front. So 12 times this 3/4 of the inner piece, 2x to the fourth plus 5, 3/4 minus 1, or 4/4, times the derivative of the inner piece. So for right now, I'm going to write just dx of 2x to the fourth plus 5, saying I have to go back and take that derivative. I haven't done it yet. So simplifying a little bit, y prime is equal to 4 goes into 12 again. 3 times 3 is 9. We have this 2x to the fourth plus 5, all raised to the negative 1/4 power, all times the derivative of 2x to the fourth is 8x cubed, which is the exact same thing that we were getting up here. So multiplying 9 times 8x cubed is 72x cubed, bringing down the piece that had a negative exponent to the denominator and rewriting it as a radical. And I'm just kind of skipping all those steps I did before to show it. So it doesn't matter which way you decide to do it, you're going to get the same results either way. So you'll see that sometimes it's also helpful to not always go and take the derivative of every piece like we're supposed to do. And sometimes just write in that we're going to come back and do that so that you just don't have too much going on and you don't miss something. Okay, so let's jump into one that has a little more going on in there. This one just had the chain rule that we had to use, but maybe we have multiple rules that we have to use when we're taking the derivative. So for instance, what if we had y is equal to x cubed plus 2, and then that's all in parentheses, and now we have another parentheses outside, so times parentheses x squared minus 1, all raised to the 4th power. And so we want to take the derivative by dy dx. So I notice I have multiplication in here. I really don't want to have to distribute out x squared minus 1 times x squared minus 1 times x squared minus 1 times x squared minus 1, and then multiply by this parentheses. We could do it, it just would take a while. So we have to use our product rule. And so when we're using the product rule and we take the derivative of this piece, we need the chain rule. So on this piece, when we take the derivative, we're going to need the chain rule. So dy dx. So right now I'm not going to take the derivative of anything. I'm just going to write out what we would do using the product rule. So derivative of the first. So I'm going to say d dx of the first, which is our x cubed plus 2 function, times our second function. So not doing anything to that. We're just going to multiply it by x squared minus 1 raised to the 4th. Plus the first function, which was the x cubed plus 2, times the derivative of the second. So d dx of the second, which is x squared minus 1 to the 4th. Okay, so let's look at the derivative of our first piece. So derivative of x cubed plus 2. So hopefully you got 3x squared. All times the second function, x squared minus 1, all raised to the 4th. Plus our first function, x cubed plus 2. Okay, so we need the chain rule when we take the derivative of this piece. So the derivative of the outer, so the outer piece is the parentheses raised to the 4th power. So this would be times, bring our power down front, 4 of the inside, x squared minus 1. Subtract 1 from our power. But we need to multiply by the derivative of the inside. So let's just write that we're going to do that, d dx, and we'll come back to it. All time, the derivative of x squared minus 1. Be careful, you cannot distribute this 3x squared inside this parentheses because it's raised to the 4th power. So we're just going to leave it alone, and we're just going to say, well, this is the same thing as, I guess you don't need the parentheses, 3x squared all times x squared minus 1 to the 4th. See if we can clean this up a little bit. Let's bring this 4 out here. So this is plus 4 all times this x cubed plus 2 all times this x squared minus 1 to the 3 minus 1 power. I'm sorry. This should have been 4 minus 1. I was probably calculating it in my head. So 4 minus 1 is 3. So this should be a cubed times the derivative of x squared minus 1. So the derivative of that is just 2x. So we got 3x squared all times x squared minus 1 all raised to the 4th plus, I'm just going to pull this 2x because it doesn't matter the order that we multiply things. I'm just going to pull the 2x in front and multiply it by the 4. So 4 times 2x, this is an 8x, all times x cubed plus 2, all times x squared minus 1 to the 3rd. I'm just curious how far they took it. So right here, and it's not like I'm trying to solve. Later on, we're going to try to figure out when our derivatives are equal to 0. So right now, I don't really have to worry about that. If I had to figure out when this was equal to 0, I would start factoring. But let me just pause and see how far they took it. But I think we can leave it like that. Okay, so I just wanted to make sure how they were expressing their answer, and they did take it further. And I can see why they would want to do that, because there's going to be a time very soon that we're going to start solving for when these are equal to 0. And so we need to be able to simplify and factor. And so looking at this derivative, notice that we have this, what's inside this parentheses? X squared minus 1 to the 4th. And this piece over here, notice that this has a x squared minus 1 cubed. So we can actually factor out 3 of those parentheses, x squared minus 1 quantity cubed. If I look at anything else that they have in common, notice here we have an x squared. And here we have a single x. So what they share in common is one single x. Let's pull that one single x out. They share an x squared minus 1. The most that they share in common, though, is 3 factors of that. And that's all that they share in common. So if we pull that out of this piece right here, notice that we have a 3 that's left over. We have a single x that's left over. And we only pulled out the cubed, and this is raised to the 4th power. So we have one of these parentheses, x squared minus 1 left. Plus, so same idea, let's look at what we pulled out from this grouping. So we pulled out the x, we're left with that 8. We have that x cubed, x cubed plus 2. But we factored out x squared minus 1 quantity cubed, so there's just 1 left there for that piece. I don't have to write it. So we can simplify inside that bracket by distributing. So So I can take this 3x and I can distribute it to each piece in here. And I can take this 8 and I can distribute it to each piece in this parentheses. So we have x all times this x squared minus 1 cubed, bracket 3x times x squared. So that is a 3x cubed. 3x times -1 is -3x. Distribute our 8. So we have plus 8x cubed plus 16. So we have x all times x squared minus 1 quantity cubed, all times. So we have a 3x cubed plus an 8x cubed is 11x cubed minus 3x, because there's no other x terms inside that bracket, plus 16. Darn it. So any questions on that one?
I have one.
Okay.
So I see where you circled the 3x and the 8.
Right.
I know it has something to do with the x's, but what happened there? Why is it not 3x squared and 8x?
Okay, because from this piece right here, when we took the derivative, we are factoring out what they have in common. So looking at what this group has in common with this group. And so notice that this has an x squared in this group and this has an x. And so we're pulling out the most that they share in common, which is one single x. So I was pulling out an x here, just one of them, and which left me with a single x here. And I needed that 3 in front. Where here I was pulling out an x. And so if I pull out that x, it's just left with a 8.
Oh, okay, I see, because you put the x that you pulled in front where the pink bracket is. Okay.
Yeah,
Okay,
right here. And then because what's inside these parentheses, x squared minus 1, each of those groupings have an x squared minus 1 in parentheses. But there's 4 of them here and 3 of them here. So I pulled out 3 of these from each piece, which would leave 1 left here. No more, there's none of those left in here. And we still have that x cubed plus 2.
Okay,
so it's just factoring what they had in common.
Yeah. Okay, thank you.
You're welcome. Any other questions? I'm sure she was not the only one that didn't get that or didn't see it at first. So if it takes you a second just to look at it, that's fine. Joy, mute and unmute.
Sorry.
No worries.
Curious as to how do we know when to take it further, because you even had to stop and check.
I know, exactly. That's a good question. So basically at this point, I would be so happy that you got to hear.
Yeah.
Especially right now, but we are going to need this when we get into the next chapter. We start graphing these functions. We're going to need to figure out when these things are equal to 0, because those are actually remember, taking the derivative are slopes of our tangent line or slopes at particular values on our graph. And so if we graphed a function and we found that our slope was 0, then usually what's happening there is we have a max or a min value. Not necessarily, but a lot of times we do. And those are important things that we a lot of times want to figure out in application problems, like where are we going to maximize profit or where are we going to minimize our cost. And so these are areas when trying to find when the derivative is equal to 0. And the only way that we can do that is to go further from this point here and to be able to factor it so that we can set this equal to 0. Because if I set this equal to 0, I would not be able to solve for x, where if I set this equal to 0, I should be able to solve for x. I might have a little bit of problem here without using college algebra, but I would be able to do it. I know that you guys don't necessarily have college algebra behind you, or you might not know how to factor this, so I wouldn't expect you to have to figure out that 0. Although if it does ask you when that is equal to 0, I would let you use a feature, and I wouldn't put that on the exam, but I would let you use that feature of Desmos.com. So let's just do that real quick. Let me pause the video while I pull that up. So I just went to Desmos and I plugged in the equation that factor 11x cubed minus 3x plus 16, so we could figure out when this was equal to 0. And so right now I can do that by graphing it and just going to the x-axis. I see that I have an intercept here and it tells me what that point is. So I know it's when x is about negative 1.213. It could be rounded, I'm not sure. But that, again, that's something that we're going to be needing to do later in the next chapter, finding out when our derivative equals 0 so we can find that max or min or find where our graphs are increasing and decreasing. Okay. Good questions. Okay, so let's maybe look at one more. It has multiple things going on. So we have, I'm just going to say f of x. We have it in terms of t. F of x is equal to 2x plus 3. That whole quantity is cubed. And then all over 4x squared minus 1. Okay, so notice there we have division. And so we are going to need to use the quotient rule. And within that quotient rule, notice our numerator, we have this polynomial cubed. So we're going to use the chain rule there. So let's just write out what we're going to do, which derivative we're taking where. So the derivative of f of x. So quotient rule says the derivative of the numerator. So I'm just going to say d dx of my numerator. I'm not going to take it yet. So 2x plus 3 quantity cubed times our denominator, which is our 4x squared minus 1, minus the numerator, which is that 2x plus 3 quantity cubed, times the derivative of the denominator, so d dx of the denominator, which is 4x squared minus 1, all over that denominator, which was 4x squared minus 1 quantity squared. So chain rule here. When we take the derivative of 2x plus 3 quantity cubed. So I'm going to bring down my power, 3, of the inside, 2x plus 3. Subtract 1 from my power, so that's now a square, times the derivative of the inside. So times d dx of the inside, which is 2x plus 3. Times the denominator, 4x squared minus 1, minus, so that numerator, which was the 2x plus 3 quantity cubed, and the derivative of 4x squared minus 1. So general power rule, bring down the 2. 2 times 4 is 8. So this is just 8x. Derivative of constant is 0. All over this 4x squared minus 1 quantity squared. So I have 3 times 2x plus 3 quantity squared. The derivative of this piece, 2x plus 3, the derivative of 2x is just 2. Derivative of 3 is 0. Times 4x squared minus 1 minus 2x plus 3 cubed times 8x. All over 4x squared minus 1 quantity squared. So notice that there's values in common on top. Let me just change that. That we can factor out. I don't know if we want to change it around a little bit, but notice that inside this parentheses, you have the same exact thing. And we can pull out 2 of them. The other thing that we have in common is a 2. So we can factor out a 2 from 2 and 8. So if we factor those out in the numerator, so pulling out a 2, pulling out the parentheses 2x plus 3, quantity squared. Okay, so if we pull that out right here, this 2x plus 3 quantity squared, we pulled out this 2, so we're left with a 3 out front, and we're left with this 4x squared minus 1. So parentheses 4x squared minus 1. Minus, well, we pulled a 2 out of the 8, so I'm left with a 4 there. I'm left with an x. And I pulled out 2x plus 3 quantity squared. And I have a cubed here, so I'm left with 1 parentheses 2x plus 3. Bracket all over 4x squared minus 1 quantity squared. Okay, so we got 2. It keeps doing that. All times 2x plus 3. Quantity squared. So I'm just going to distribute here. So let's distribute our 3. So 3 times 4x squared, that is 12x squared. 3 times negative 1, so minus 3. Make sure you carry the negative when you distribute the 4x. So negative 4x times positive 2x is negative 8x squared. So minus 8x squared. And negative 4x times a positive 3 is negative 12x. All over the denominator, 4x squared minus 1 quantity squared. So you have 2, all times 2x plus 3, quantity squared. Combine like terms inside this bracket. So 12x squared minus 8x squared, that's a 4x squared. And we have minus 12x minus 3. All over 4x squared minus 1 quantity squared. That's not a 30, that's a parentheses. Okay, so again, I took that a little further on the top to rewrite it as completely multiplied together, so that as factors. And again, that's because later on, we're going to try to find for rational functions like this, when we get a derivative as a rational function, we're going to find out when is our derivative equal to 0 and when is our denominator equal to 0. So it's helpful to be able to factor. Okay, so we're going to throw some more stuff at you, just review stuff. Hopefully you remember how to do it. So taking what we're doing and then finding the equation of the tangent line. So we've done tangent lines before. So we know we have to find the derivative, then we have to find the derivative that evaluate a specific value of x that gives us the slope of our tangent line. So we're given that f of x is equal to x cubed plus 7 to the 2/3 power. So plus 7 in your parentheses, that x cubed plus 7 is all raised to the 2/3 power. So find the equation of the tangent line at x equals 1. So we need to figure out what the slope is of the tangent line at x equals 1. So we need to take the derivative of f of x. We were going to use our general power rule. So our outer function is the parentheses all raised to the 2/3 power. So f prime of x, bring our power down front. So I'm bringing my 2/3 down front. Of the inside, nothing changes with the inside, x cubed plus 7. Subtract 1 from our exponent. So 2/3 minus 1, but I'm going to write my 1 to have a common denominator, so 3/3. Times the derivative of the inside. So we can do it now, or we can write that we're going to take the derivative. Let's just do it now. Derivative of the inside, x cubed, is 3x squared. So notice you have a 3 right here in the denominator and a 3 up here in the numerator. So those 3's are going to cancel. I'm just going to pull the x squared out front with that 2. So this is 2x squared parentheses x cubed plus 7 and parentheses 2/3 minus 3/3 is -1/3. Let's bring down the negative exponent to bring it positive. So we have the 2x squared in the numerator all over x cubed plus 7 to the positive 1/3 power. Might as well leave it that way. If this had a radical to start with, I might rewrite that as a radical. Excuse me. But we want to know what's happening when x equals 1. So we want to look at f prime of 1. So let's go in here, wherever we see an x, let's put parentheses and we'll go back and put 1. So we have 2, I see an x, I'll put parentheses and square that parentheses. All over, I see an x, so we're going to put parentheses and we're going to cube it, plus 7 to the 1/3. So order of operation, square 1, we get 1. 1 times this 2 is 2. All over, inside this parentheses in the denominator, 1 cubed is 1 plus 7, so that's 8, all raised to the 1/3 power. Same thing as cubed root of 8. So what can I cube to get 8 is 2. So the derivative of the function at x equals 1 is actually 1. So the slope of our tangent line at x equals 1 is 1. But in order to find an equation of a line, we need a point. And we can find that point by plugging in our 1 wherever we see an x in our original function. So this is equal to our original function, parentheses, I see an x, I'm going to put parentheses there, cubed, plus 7, all raised to the 2/3 power. So if I cube 1, I get 1, plus 7, I get 8 to the 2/3. Another way to rewrite this is cubed root of 8, and then we can square it. I'd rather square it after. So what can we cube to get 8, which is 2? And then that square, so 2 squared is 4. So we have our slope, and now we have a point. When x is 1, our y value we found was 4. So using that, we know what our slope is, what our point is, we can find the equation of a line. I tend to like to use the y equals mx plus b and just solve for b first. So our y value is 4. Is equal to our slope, which we said was 1, all times x, which we is 1, plus b. So 4 equals 1 plus b. Subtract 1 on both sides, we get b is 3. So the equation of the tangent line on that curve at x equals 1 is y is equal to our slope, which is 1 times x, 1x or x, plus b, so plus 3. So questions on that one?
I have a question. I just think I missed it when you put the 3x squared on the top part. Where did you get the 3x from?
Right here, because we had to take the derivative of the inside of the function. And so the derivative of x cubed, bring the power down front, is 3. Subtract 1 from the power is a square. And then the
Oh,
derivative of constant
okay,
is
I see
0.
it. I just missed it when you said it at first, so I was just lost in that part. Thank you.
Yeah, no worries. Other questions on that? Okay, so let's look at another example. And here's the example where we're trying to find where the equation of the tangent line is horizontal. So find all values of x for which the given function where the tangent line is horizontal, and we're given that f of x is equal to the square root. And then underneath that square root, you have an x cubed minus a 6x squared plus 9x plus 1. So find where the tangent line is horizontal. Okay, so horizontal lines have a slope of 0. So we want to find all values of x such that our derivative is equal to 0. Okay, so before we take the derivative of that, let's rewrite it. So we can rewrite f of x instead of writing it with a square root. We can rewrite that as x cubed minus 6x squared plus 9x plus 1. And this is all the same thing as square root is the same thing as all raised to the 1/2 power. So we want to use our chain rule when we take the derivative. So the derivative of the outer, so bring down the power 1/2 of the inside and subtract 1 from our power. So 1/2 minus 1, which I'm going to write as 2/2. Times, we can't forget that we need the derivative of the inside. So d dx of our inside, x cubed minus 6x squared plus 9x plus 1. So we got, this is going to end up being a negative 1/2 power. And so I can bring that down to the denominator. So I'll have this 1 up here in the numerator all over this 2. And this is going to be negative 1/2 power, so bring it down, that's positive 1/2. So x cubed minus 6x squared plus 9x plus 1 to the 1/2 times, so derivative of the inside. So derivative of x cubed is 3x squared minus the derivative of 6x squared is 12x plus the derivative of 9x is 9 and the derivative of 1 is 0. So 1 times that derivative of the inside is the derivative of the inside, 3x squared minus 12x plus 9, all over 2, and I can rewrite the 1/2 power as a square root of this x cubed minus 6x squared plus 9x plus 1. So we want to know when f prime of x equals 0. So we want to know when is this whole thing equal to 0? Yeah. Let's just do it this way. So 0 is equal to this. So technically, we can clear our fraction. This is an equation, so what we do on one side, we can do on the other. We can multiply both sides by this 2 square roots of, so our denominator to clear it. So x cubed minus 6x squared plus 9x plus 1. Whatever we do to one side of the equation, we got to do to the other. Well, anything times 0 is 0. So we got 0 is equal to, and then over here, the whole point of that was so that our denominator would go away. So it's equal to our numerator. So 3x squared minus 12x plus 9. Okay, so a couple ways. I see that that's quadratic. There's a couple ways we can approach solving quadratic equations. One of them is factoring, doesn't always work. One is using the quadratic formula, but I noticed that this probably does factor. And I noticed that 3x squared minus 12x plus 9, first thing you want to do when factoring is see if we can pull out anything that they all have in common. And they all have a 3 in common, so I can pull a 3 out of all 3 of those terms. So if we pull 3 out of the 3x squared, you're left with x squared. Pull a 3 out of negative 12x, you're left with negative or minus 4x. And pulling a 3 out of the 9, we're left with plus 3. So doing that, my coefficient in front of x squared is 1, and that's the easiest case. So you're thinking what two numbers multiply to 3 and add to negative 4? Multiply to a positive 3, add to a negative 4. Is negative 3 and negative 1? So once it's set equal to 0 and you factor the one side completely, set each factor equal to 0. Well, 0 can never equal 3. So there's no value to solve for x there. We're looking at when is x minus 3 equal to 0. Solve for x, add 3 to both sides, you get x equals 3. And when is x minus 1 equal to 0? Add 1 to both sides, you get x equals 1. Okay, so we just found out the values where the equation of our tangent line is horizontal. So f of x has horizontal tangent lines here. Okay, so that's going to be something we're going to be doing a lot of in the next chapter when we start graphing these functions. We got to find when is that derivative equal to 0. And then that's going to give us ways to figure out, is there a max min, where is it increasing, where is it decreasing? So maybe one more like that. So same principle, we're trying to find out when our function has a horizontal tangent line, but this time f of x is a rational function. We have x all over x squared plus 4 raised to the 4th power. So we're going to need to use our quotient rule, and we're going to need to use the chain rule when we take the derivative of the denominator. So quotient rule, derivative of the top. Do we need to write that down? So derivative of the top, so d dx of x, all times the bottom, x squared plus 4 raised to the 4th, minus the top, which is x, times the derivative of the bottom, so d dx of x squared plus 4 all raised to the 4th, divided by x squared plus 4 to the 4th, but this is all raised to the 4th power. I'm sorry, not all raised to the 4th power, it's all squared. Well, the derivative of x is just 1. All times x squared plus 4 to the 4th minus x. And so the derivative of the denominator, we need to use the chain rule. So bring our power down front, the outer function. So 4 of the inner front piece, x squared plus 4, subtract 1 from our power, which is 3, times the derivative of the inside. Let's just say that we're going to come back and do it. So d dx of x squared plus 4. All over the denominator squared. So rules of exponents, power to power, you multiply. So we can rewrite this as x squared plus 4, that whole quantity raised to the 8th power, 4 times 2 exponents. Okay, so we're left in the numerator, x squared plus 4, all raised to the 4th power, minus x times 4, or 4x, x squared plus 4 quantity cubed times the derivative of the inside. So derivative of x squared is times 2x. The derivative of the constant is 0, all over the denominator squared. Which ended up being x squared plus 4 raised to the 8th power. Okay, so we want to find when is this equal to 0? And so this is where factoring, and we can either do it now or we can do it later. Notice that what's inside the parentheses here, this x squared plus 4, it's the same thing we have over here, x squared plus 4. But we have 4 factors here and we have 3 factors of it here. And so we want to pull out what they have in common. And so notice they have 3 of those in common. So we're going to pull out an x squared plus 4 quantity cubed. If we do that from this piece, you're left with 1 there. So x squared plus 4. Minus, well, I pulled them all out of this. So I'm left with a 4x times a 2x. Well, 4x times 2x is 8x squared. All over x squared plus 4 raised to the 8th. Notice this is now multiplication, and we have same factors in the numerator and denominator. We have an x squared plus 4 quantity cubed up here, and we have an x squared plus 4 raised to the 8th power in the denominator. So we're going to use rules of exponents. Same base. If our denominator has the higher power, if n is bigger than m, then we can rewrite this as 1 over b to the n minus m power. So subtracting the exponents. So I'm left within the numerator, and maybe we can just combine like terms while we're at it. We have an x squared minus an 8x squared. So this is a negative 7x squared plus 4 all over. So if I subtract 3 from 8, that will leave me with 5 of these left over. So it's all over x squared plus 4 to the 5th power. Okay, so that was just taking the derivative. So now we need to find when f prime of x is equal to 0. So we need to know when is negative 7x squared plus 4 all over this x squared plus 4 to the 5th equal to 0. Technically, you have a rational function. You're trying to find when that's 0. Really, you're just looking at when is that numerator equal to 0. We know that if we have a 0 over a number, this is equal to 0, where the number cannot be 0. 0 over x. So I can multiply both sides by my denominator. That would clear it over here. 0 times the denominator would give us 0. That's another way to think of it. So we have negative 7x squared plus 4 is equal to 0. Quadratic equation, multiple ways to approach this. I can try to factor it. I can use the quadratic formula. I notice it's in the form that I can use my square root method if I just isolate this square here. So let's just do that. That's the fastest, easiest way I see. So let's subtract 4 on both sides. We get negative 7x squared is equal to negative 4. divide both sides by -7. We get x squared is equal to, well, -4 over -7 is actually +4/7. Now that we isolated the square, we can use the square root method. So we can take the square root of both sides of our equation. But when we take the square root of both sides of our equation, we want to make sure that we put a plus or minus, and I usually put it in front of the radical with the square root of the constant. So we got the square root of x squared equals plus or minus the square root of 4/7. Well, what can I square to get x squared? Well, that's just x is equal to plus or minus. There's rules that says if you have square root of a fraction, that's the same thing as the square root of the numerator, 4, all over the square root of the denominator, 7. Square root of 4 is 2, all over √7. So there's two places where this function has a horizontal tangent line. And that would be at x equals +2/7, or not 2/7, 2 over √7, and -2 over √7. They might ask you to write it as, put a comma in between your answers if there's multiple answers. So any questions on that one? So that is the chain rule. You guys ready for derivatives of exponentials? No. Let's see. Okay. I'm not sure which ones we want to do. So Katie and Sarah are working on taking the derivative of f of x. Let's just do one more. Is equal to 2x all over 3x plus 4. Katie uses the quotient rule. To get the following. So this is her work. So she says f prime of x is equal to 3x plus 4 all times 2 minus 2x times 3 all over 3x plus 4 quantity squared. From there, she gets that this is equal to 8 all over 3x plus 4 quantity squared. Sarah, she converts hers, converts it into a product and uses the product rule and chain rule. So Sarah rewrites f of x as a product of two functions. So she rewrites it and uses the product rule. And chain rule. So taking this function f of x, she's like, okay, we can move our numerator up into the denominator by just changing, putting a parentheses around it and rewriting it to have, this is to the first power. So bringing it up to the numerator would make it to the -1 power. So she's like, okay, well, f of x could be rewritten as 2x all times parentheses, that denominator 3x plus 4 raised to the -1 exponent. So once she did that, she's using the product rule and she found that f prime of x equals 2x times -1 times 3x plus 4 to the -2 times 3 plus 2 parentheses 3x plus 4 to the -1. So she simplifies and says, well, this is the same thing as 2 all times 3x plus 1 to the -1 minus 6x all times 3x plus 4 to the -2. Okay, explain your discrepancies between the two answers. Which procedure do you think is preferable? So which way would have you preferred to do it? Quotient rule or product rule? Okay, so we got two separate things. We got f prime of x, this right here. And we get, that doesn't work. Try that again. And we got f prime of x. Let me just put it right here. Okay. Anyone look preferable?
Well, the one on top looks a lot easier.
This one looks, the second one, right? That looks a lot really messy. It's not, this is not a great form. And that should have been a 4 here. Of solving it for 0. But we could manipulate and show that this is actually the same thing. This one, to solve for 0, we would just have to set the numerator equal to 0, and it's actually impossible. 8 is never 0. Yeah. So I would really have to do a lot more work on that second one to clean it up. And I would probably want to clean it up because I have negative exponents. I didn't start with negative exponents. I can prove to you that that's the same thing. Let's just do it real quick. So bring this down to the denominator to make that exponent positive. So I have 2 all over 3x plus 4 minus, I have a 6x all over, bringing down this negative exponent to make it positive, 3x plus 4 squared. In order to add 2 fractions, we need a common denominator. Our least common denominator, well, they have the same factor, it's just that this one has 2 of them. So we need 2 factors of 3x plus 4. So 3x plus 4 quantity squared is our LCD. So multiply the fraction that has a missing piece. So it needs another 3x plus 4. Let's multiply that by a fancy one, 3x plus 4 over 3x plus 4. So let's distribute our 2. So we got 2 times 3x is 6x. 2 times 4 is plus 8. And then the other numerator is minus 6x. All over our LCD, which was the 3x plus 4 quantity squared. Combine like terms in the numerator, 6x minus 6x cancels. So we're left with 8 all over 3x plus 4 quantity squared. Which is the exact same thing that we got above. Okay. So we only did 4.3 this week, the on-chain rule. So that's the only homework that you should have due on Monday. Couple things that you might be helpful for you guys for next week is review rules of logs. Logarithms. And exponential functions. So we'll start talking about, or we'll learn how to take the derivative of exponential functions, e to the x. It's actually the easiest one ever. It's just itself, e to the x. How to take a derivative of some value a, some constant a raised to the x power, where a is bigger than 0, and then natural log and logs. So being familiar with knowing what those are is really helpful. And exponential functions are used a lot to represent real life situations. Okay, so let's stop there for the day.